Hello, everyone. Welcome to the fifth MultiScale Talk given by Professor Karl F. Böhringer. Professor Böhringer obtained his university degree in computer science, or in German, Diplom Informatiker, from the University of Karlsruhe, Germany, and both his master's and PhD degree also in computer science from Cornell University in New York. He was a visiting scholar at Stanford University and a postdoctoral researcher at the University of California, Berkeley. Since 1998, Professor Böhringer is at the University of Washington in Seattle, where he is a professor of electrical and computer engineering and bioengineering, as well as director of Institute for Nanoengineered Systems. Professor Böhringer has held visiting faculty positions at the University of Tohoku, Tokyo, and Kyoto, all in Japan, as well as Sao Paulo in Brazil and École Polytechnique Fédérale de Lausanne in Switzerland. Today, Professor Böhringer is going to talk about moving drops on microstructured surfaces. So, Professor Böhringer, the screen is yours.
Well, thank you very much, Zoran, for the introduction. I'm very happy to be here today. I hope that you can see my screen. I would like to tell you about interesting behavior of drops as they move on microstructured surfaces. This is a topic that we've been studying for quite a few years, and several of my students have written papers on that you can see in the literature over the past decade or so. So I think many of you have seen pictures like this where you have a water drop sitting in almost spherical shape on a hydrophobic surface, in this case a lotus leaf, and people often talk about the lotus effect, where drops are suspended on the surface almost without, with very little contact to the actual surface, and they can roll off that lotus leaf very easily. Many people have been wondering about the reasons for this kind of behavior, and if you zoom in and look at the lotus leaf surface at the microscale, then you see this almost fractal-like structure with roughness at different scales, both at the micro and the submicron scale. We've learned that this behavior, or this structure, really explains a lot of the behavior of these so-called superhydrophobic surfaces, where the drop is making contact with the solid only in the very top of these rough surfaces. Now, as engineers, we are interested in creating similar kind of behavior, but also taking advantage of it for particular purposes. And really, over the past few decades, people have studied this effect and related kinds of surface engineering. For example, from George Whiteside's group, there was a paper now almost 30 years ago where they demonstrated that you can create a hydrophilic gradient that makes the drop move uphill against the force of gravity. About 10 years later, there was beautiful work from Duke University of drops moving on a surface where you have strong localized electrostatic fields, so electrowetting that drives drops from one location to the next. Heiner Linke showed that you can make also rough surfaces or asymmetric surfaces and have drops moving on them when you heat these surfaces with the so-called Leidenfrost effect. And finally, there was a more recent beautiful work by David Carré and several of his collaborators demonstrating that actually shorebirds take advantage of these kind of effects by moving their beak and transporting small amounts of water into their mouths this way. What's behind that? There's just a little bit of theory that I want to remind you of. Probably many of you have seen Young's equation that essentially relates the shape of a drop that sits on a surface with the particular material properties or the surface energies. And we distinguish between more hydrophobic surfaces where you have a large contact angle, so the theta C in this particular diagram, and more hydrophilic surfaces like you can see here, where the contact angle is smaller. This angle can be calculated as a function of surface energies given by these parameters gamma for solid gas, solid liquid, and liquid gas. And now, this equation holds primarily for flat surfaces, but you can actually extend this equation to rough surfaces as well. And that's what we're really interested in today. So here is an engineered rough surface where we basically describe the roughness with two parameters. It actually turns out that we need primarily the factor phi, which looks at the pillar top surface. So what I've shown here with red, or you can think of it as the mesa, the top of the pillars. And you put that into relation with the total projected area, so the entire surface that's blue here. And of course, this number is always less or equal to 1. So if you have a flat surface, you have 1. If you have a very spiky rough surface, you have a very small, but still positive phi. You can also ask about the sidewalls or the height of these pillars. There is another parameter r. It turns out that we don't need that number later on. So for now, let's just remember the number phi. Now, how can we describe the contact angle on a rough surface? Well, many years ago, Cassie and Baxter published a famous paper that shows a very simple relationship, and actually very intuitive relationship, because they found that the contact angle, the apparent angle on a rough surface, basically is the weighted average between what you would get at a solid surface and, well, as opposed to basically a perfectly spherical drop suspended in air. So you essentially just look at the ratio between the contact area, which is given by phi, and all the areas that are not in contact. So that's 1 minus phi. You can simplify this equation, and what you find out is that a rough surface essentially makes itself appear more hydrophobic than a flat surface with the same material. Now, we can take advantage of that property by engineering the surface or the surface geometry so that you can get a more rough, or less hydrophobic surface depending on the roughness. So remember how we calculate phi. We can make this a function of location. So you can make phi larger or smaller depending on how you pick your geometry on the surface with the parameters A and B. A, the surface area of the mesa, and B, the gap between them. So if you make A very small and B large, then you get a very small phi, and accordingly you get a larger contact angle that makes the drop appear closer to a sphere. Now, we can create gradients by varying this parameter phi, and you can demonstrate that a drop follows that gradient. You have to give it some vibration so that it overcomes the hysteresis that you often have in these kind of systems. But in a control experiment, you can create two different gradients in opposite directions, and then you can eliminate any bias that you could possibly have by gravity and have drops move in opposite directions. Now, of course, these gradients are not very long, so the drops don't travel very far, and the usefulness of the system is somewhat limited. So we were interested in looking at ways to make the drops travel larger distances. And instead of a gradient, we created a ratcheting surface. So a system where the drop is repeatedly following essentially small steps, small gradients. This is a system that my former student Yegan Erdem and several other colleagues and former group members worked on. Yegan is now a professor in Turkey and still interested in microfluidics in various contexts, including a recent paper on a model for the system that came out in Langmuir just a few months ago. So you can see in this picture there's an asymmetric surface pattern and a even more spiky surface on the left and the right to that track. And this asymmetry essentially creates an asymmetric force also on the footprint of the drop. If you look at this in the video, and I hope that you can see this on your screen as well, you can see a high-speed recording of a drop. Again, it is vibrated slightly, and during the vibration, it makes step-by-step progress from the left to the right as it moves on the surface. In this case, the features are too small to be resolved in the video, but you can see the trace with tiny amounts of liquid left behind by this drop. So this was also published a few years ago, again, by a former student, Todd Duncombe and colleagues in Advanced Materials and Langmuir. You can model that. I will not go much into detail on that, but essentially you create a mass spring damper system where you model the forces that are acting on the footprint of the drop, and you relate that to the inertial forces of the center of mass. If you model that, then you can actually show that the anisotropy of the surface translates into a lateral force that makes the drop move from, in this case, from left to right. And here, since it is a ratcheting motion, there's no limit on how far the drop can move. You can also demonstrate that the drops are responding to different frequencies depending on their size. Again, it's a mass spring damper system with larger mass responding to lower frequencies. So you can actually address drops based on their volume. So for example, for smaller drops, like here in this diagram with 13 microliters, you have a range of frequencies to which these drops respond and start moving. But this range is offset from other drops with a smaller volume. So for example, you can pick a frequency maybe around 40 hertz where only the large drops are moving and the small drops do not, or vice versa. So you can, for example, merge drops by having a small drop move towards a large one, or you can pick a frequency where both of the drops move at the same time. After they merged, you can lower the frequency and then make both of the drops move or the merged drop move simultaneously. You can also work with different viscosities and like in this example, mix water with glycerol. Now, what's maybe even more surprising is that you can make this droplet transportation system work in some very unexpected ways. For example, here you see drops that are moving in this troposcopic image on the top of a surface. This is made with PDMS, but also hanging drops that are clinging to the surface roughness, even though we think of the material as super hydrophobic, but at the same time, the roughness creates pinning forces that's where the drops essentially are holding on and moving from the left to right here for the red drop, from right to left for the blue drop. And now, I want to show some application of this technology, and in particular, I want to go to a much larger scale now. So what you're seeing here is solar panels on the left side dirty, on the right side clean panels, and this is actually a very large problem with a lot of energy being lost because solar panels get dirty over time. They're often in dusty areas. Now, we demonstrated that you can also create these kind of anisotropic surface patterns with transparent materials. So simply by having a contrast between more and less hydrophobic coatings. We shown that with drops that are moving on these small surfaces. I just show very briefly the modeling that we do, looking at the different forces. And in this particular case, we have a drop that's actually suspending small sand particles and is still moving from left to right, even with a pretty hefty load of sand here with 2 milligrams in in about a 10 microliter or 10 milligram droplet of water. Here's a video of this system, and I've already run one video where one drop has been moving and cleaning one area with such a coating. Here's the second drop, and this is in real time. The drops are moving along on this predefined path, picking up dirt along the way. While it's doing that, it's slowing down because the drop is getting heavier and also more viscous in this particular case. We can clean an area of about a square inch or 5 square centimeters in a few seconds. So you can extrapolate from that and see that with about 100 droplets of just 1 milliliter, you can clean an entire typical solar panel with about 2 meters squared. Here's a demonstration of how this could also be done. So again, we have a drop of water on a small solar panel in this case, just a lab demonstration. And while it's moving along, picking up the dust particles, you can see that the efficiency of the solar panel output is, or solar cell output is increasing. If you look at the diagram overall, we go from about 70% to 90% by having a clean versus a dusty photovoltaic cell. Just a few more words that besides vibration, you can also create systems where these drops are moving with electrostatic forces. So it's a combination of these ratcheting patterns, anisotropic ratchet conveyors, and electrowetting where we're driving the drops in particular directions. So here we demonstrated that we can move them in opposite directions depending on how we pattern the surface. Now we're currently looking at larger scale applications to work with solar panel manufacturers for cleaning large solar panels. This is work in progress. I want to come to my conclusions today, again saying that really interesting things can happen at the micro scale if you create and engineer surfaces and the interaction between liquid, solids, and gas. In particular, we created these anisotropic ratchet conveyors to build self-cleaning surfaces. But one other challenge that I would really like to work on is to make these systems completely self-contained and capture water from the atmosphere by condensation overnight. There are beautiful examples in nature by lizards, for example, that live in the desert that also capture humidity from the surrounding air and essentially live off that humidity. So we would like to build solar panels that again learn from nature and create their own cleaning liquid by themselves. Just a few words and acknowledgements. A lot of this work was done by my former student Dee Sun, and many other students have worked on this as well, including Hal Holmes and Amy Ahmad Shukri and many other students in my group. So thank you very much for having me here today. I'm really glad that I could tell you about this work, and maybe we have time for a few questions.
Great, thank you. Very nice body of work. Well, did you calculate because you know, like you want to clean the surface and make the production of energy more efficient. But what is the cost, energy cost for cleaning the surface? Like, do you really manage to save electricity and not to waste more?
Yeah, this is a great question, and something that we've thought about extensively. So it's absolutely true that the solar panel market is a very competitive, very low margin market at the moment, and will probably get even more competitive in the future. And any additional cost that we're adding to the manufacturing or the operation has to be very well justified. In this particular case, we calculate that we can do the cleaning within about 10 minutes. So this would be a procedure that would probably run, say, early in the morning after we collect dew, so there is a relatively short time period and a low energy cost to operate the system. Now, I showed two different ways to do that, either with vibration or with an electrowetting system. In both cases, there is energy input. For the vibration, you could actually work with a very high Q system that has a resonance frequency in that range. And actually, many mechanical systems resonate at this 60 to 80 hertz. I don't have exact numbers right now, but you can show that the energy input would be very small, or could maybe even be helped by vibrations from wind or other environmental sources. Now, the other big question is really how much does it extend the cost or increase the cost for the solar panels? And I think that's a more significant question. So the answer for that is there are solar panel coatings for reduction of reflection. So basically increasing the efficiency by anti-reflective coating. And the goal would be to increase, use the same coating to also create these anisotropic patterns. So essentially minimizing the modification of current production techniques to also integrate this capability. And this is really the key to do that. Otherwise, if you start adding more fabrication costs, then they very quickly can offset the benefits of this cleaning.
Mm-hmm. Okay. So, for example, at the moment, how do you generate the vibration? Is it that you use some piezo and then some amplifier and then, or it's like, yeah, because I think that the piezo actually, it wastes a lot of energy. Am I right?
Yeah, so the current demo systems that we have are not really designed for efficiency. So we have a vibration platform. Remember the frequencies are pretty low. They're somewhere between 40 and 80 hertz typically. So piezos are maybe not the most efficient way to achieve that, but we currently use just a regular linear electromagnetic motor to do that. Now, in larger scale systems, we would design them so that a small energy input, a small vibration could essentially bring the system into resonance and bring it into the amplitude that we need. The amplitudes that we need are in orders of tens of micrometers or possibly hundreds of micrometers. At the moment, it's the lab setup is not very efficient the way we demonstrate it right now.
Okay, so have you guys thought about some space applications regarding, I don't know, cleaning applications in space vehicles, or, for example, moving droplets there in the microgravity conditions?
Oh, okay. Well, I'm glad you asked about the space application, because we recently had some some interesting conversations with a local aerospace company. It seems like they have a serious problem about fogging in their windows. They're building a capsule for space tourists that would allow short suborbital flights. But of course, it would be very unfortunate if these passengers had fogged up windows that wouldn't allow them to see what's happening outside. So we presented some work, and I can show you one slide that I haven't shown you before that looks into cleaning surfaces, not in terms of dust, but rather in just moving condensation on that surface. The system that we tried out was a little bit different from what I've shown earlier, but the drops are, again, moving on these anisotropic patterns that are in this case transparent. We apply voltages that are pulsed that cause the drop to move sideways in this particular picture. And I have a video here that just shows very briefly how this could look like. So there is a drop moving along the surface with these pulses that we given, and you can see that the condensation is basically collected into one large drop that would, in a real system, then fall off or be collected at the edge of the window. So very exciting application currently under in conversations on this technology, and we'll see whether this will actually go into space in the coming years.
That's pretty interesting. Very nice. And actually, your system looks pretty simple. You know, just Arduino components, voltage amplifier, and a function generator.
Yes, and I mean, this was built very quickly by my student in his last months for his PhD, where we said, let's try another idea. And there was really a sequence of different design variations that we explored. And there are several papers that came out in that year, like this JMEMS paper in 2020. There are several other papers on related topics in applied physics letters and several other journals as well.
Also on this topic, do you think that also this icing research, kind of ice-phobic surfaces or ice-philic surfaces, might find a role in space applications?
Yeah, that's another great question. And of course, de-icing is really important in aerospace. Now, we've been very interested in that as well, basically preventing the icing before it even happens, because once the water is frozen, then of course, this approach does not work anymore. But I believe what we can do is we can transport the drops away before they have time to actually freeze on the surface. So that's one thing that we're exploring. In space, of course, it would be on the inside of the capsule, where it could very well be that with the extreme temperature differences, that could also be a problem. So again, we would like to remove the condensation as soon as it forms, transport the water away, and keep the surface dry and clean.
Okay, terrific. Okay, well, I don't have any further questions. I would like to thank you again for giving a talk at MultiScale Talks. And I just wish you all the best and many other beautiful research papers to come along in the future.
Yeah, Zoran, thank you very much for having me here today for the MultiScale Talks. It was really a pleasure to present the work and have a good conversation about this work. So I'm looking forward to future events in the MultiScale series.
Yeah, thank you. Bye-bye.
Bye.